Hey y'all, Charlie Pyatt here. This episode I'm going to be revisiting a concept from my old VR headset project by making a custom fitting mask for the Quest 3. The mask is going to be driven by a 3D face scan taken off my iPhone. This project also explores the impact adaptive products will have on the industrial design field as a whole. The general idea is to create a CAD system that can take in a 3D scan from an iPhone and output a 3D printable custom VR mask. I did a variation on this concept when I built my original custom VR pass-through headset a couple projects ago. I started work on that back at the end of 2021, and at that point there really weren't any augmented reality pass-through headsets on the market. Designing and fabricating that headset was a big undertaking, and by the time I had started releasing those videos, both the Quest 3 and Apple Vision Pro had been announced. Even more surprising, the Big Screen Beyond was released, which is a VR headset that also uses a custom-made face gasket from a 3D scan. It's just great to see custom products like these making their way onto the market. All in all, it's been pretty incredible how much change has happened in just a couple years in the VR, augmented reality, and custom consumer product space. One of the things that drove me to build my AR/VR headset was to explore the idea of generative product design. I really wanted to build a software system that could take in any 3D face scan and then use that information to create a custom-fit face mask for a VR headset. The custom gasket I ended up with on my previous design turned out amazing for comfort and stability when wearing the headset and was an incredible process to explore. I was originally looking to do this custom-generated mask concept on the Quest 2, but unfortunately its design really made that impossible. You can see that the body of the headset extended all the way back to the wearer's face. This just didn't leave enough room to introduce a custom-generated face mask in the stock headset and pushed me to design and build my own custom VR enclosure. Fortunately, the Quest 3 went with a pancake lens design that made the headset way slimmer when compared to the older 2 model. It makes it a great time to revisit this project. So talking about custom-generated consumer products is actually kind of difficult right now. The concept is so new that there really isn't even terminology to talk about it. If you say custom products to most people, they imagine merchandise they can apply photos to. Coffee mugs, t-shirts, and that sort of thing. What we're talking about here is fundamentally different. It's the idea of creating a dynamic software system that can create physically unique parts for each person. It's a radical change from what exists in the industrial design and manufacturing field right now. Normal consumer products are made by coming up with a design and mass-producing copies of that single item. Custom automated mass-produced products are different. With these, a software system takes in some kind of driver data and outputs a custom part for each person. This type of manufacturing has significantly higher per unit costs, but also an increased value to the consumer because of the bespoke nature of the finished product. Custom fit products also open up a bunch of interesting material options as well. On a normal VR headset, the area touching the face is usually some kind of foam or soft material. This is to accommodate and avoid pressure points on all the different types of faces that the mask has to work on. On my last headset build, I printed the final custom mask in an elastic material, but during testing I printed it in a solid as well, and it was actually super comfortable. I ended up printing the final in an elastic more out of habit than any real need. This time around I wanted to revisit that choice and make the final custom mask out of a rigid material to save costs and simplify the build. My process for actually making this custom VR mask generation system is going to be pretty straightforward. I know that the mask will have one side that interfaces with the Quest 3. This bracket is always going to be the same on all the masks I make and will be the hard point on the design. My driving data will be a 3D face scan captured on my iPhone's Face ID. From here I'll be making my software system for creating each custom mask. The system I'm designing will basically be generating the mask between the bracket or hard point and the input scan data. This project focuses a lot on 3D scanning, so I wanted to take a second to talk about the 3D scanning options out there. There are a number of different ways to get real-world objects into 3D space on the computer, all with different pros and cons. Generally, 3D scanners can be broken into 3 basic categories: photogrammetry, time of flight, and structured light. For most of the type of work I do, I use structured light scanners. This class of scanner projects a light pattern onto an object to digitally reconstruct it as a 3D asset. Structured light systems are usually designed with a particular use case in mind. There might be 3D scanning larger parts of a car, full body scans of a person, or precision scans of small objects for reverse engineering. In this case, I'm going to be using a laser-based turntable scanner for my reverse engineering and the Face ID system built into a standard iPhone for my face scans. My higher precision laser scanner is more complicated to set up and run, but I'm only going to be reverse engineering the Quest 3 gasket part once, so this isn't too big of a deal. The iPhone Face ID scanner has a much lower capture quality, but is super accessible and will be able to capture enough information to drive my masks generator. Knowing when to use which 3D scanning technology takes a lot of trial and error, and always has trade-offs in cost, setup time, and accuracy. My first step in the custom VR gasket build is going to be reverse engineering the existing Quest 3 gasket. As mentioned, this will be the hard point that my mask is generated off of in later steps. Because I need as much detail and dimensional accuracy as possible, I'm going to be using a turntable-based structured light scanner. I'm also going to be applying some ASUB blue spray to the gasket. This matte spray will help the scanner capture as much surface detail as possible and evaporate off in a few hours or so. Unfortunately, the Oculus 3 gasket is going to be a very difficult part to scan in the best of cases. It's long, thin, and has very little surface detail, so getting a good finished mesh out of the scan is going to be a real challenge. You can see here, after I've done my complete scan and merged everything together, it really struggled to get a good part. My scanner is also pretty old at this point, and even though I have something usable here, it just doesn't have enough surface detail for what I'm looking for. Fortunately, I found a better scan of the Quest 3 gasket on Grabcad. The scan was done with a much newer structured light scanner, and you can see how much better the overall scan precision and detail is. In any case, this will actually work out great. I can reference between both these scans as I get into my reverse engineering steps going forward. Now that I have my reverse engineering scan data in, I want to remodel the interface edge of the gasket in a parametric CAD package. For that, I'm going to be using Fusion 360. As a full disclosure, I was invited to join the Fusion Creators Program after my last FPS controller video, which includes a license of Fusion 360. Special thanks to Autodesk for sponsoring the video. From here, I'm going to start my reverse engineering by bringing in my scan data into Fusion as separate parts. I can then build my new model around those meshes and have a perfect copy of the gasket in CAD. Fusion does a really nice job of handling mesh data and not just solid geometry, which is great for this application. What I'm doing here is basically going in and drawing the new bracket and catch mechanism in this new part. Then I'm going to print out a test and see if it fits back into the Quest 3. Right now I'm only printing out the most minimal parts of the bracket that come into contact with the headset. Printing any more of the bracket would just be a waste of time and resin at this point. You can see it took me a few tries to get something that latches in correctly to the headset, but all in all it went pretty quick. Just a matter of taking my time and updating my CAD model from my test prints until it all fit together. Once I had my lip edge model created, I was pretty much done with my parametric CAD in Fusion. With my gasket hardpoint done, I need to get an initial face scan for the build. For this, I'm going to be using the Face ID True Depth Structured Light Scanner on my iPhone. You can see the structured light pattern on my face as I take the scan here. This pattern is usually invisible to the naked eye, but I'm using an infrared camera to capture the pattern. The scanning software I'm using is the Ethan Makes 3D Scanning app, which does a really good job of pulling in face scans and has a bunch of nice export features. All around, it's perfect for my needs, and the link is in the description if you want to give it a try. I did a quick export, and now I have a pretty good head scan that I can use for the rest of my mask creation process. Now I have my finished bracket for connecting my custom masks to the Quest 3, and I have my face scan data. Before I get into creating my mask generation system, I have one more step to do. The custom VR mask system I made a couple years ago worked pretty well, but it's really struggled with reliability. I could get it to work on my scan, but when I loaded in other people's, it was super inconsistent and would fail more often than not. I want this one to be more reliable and work with a wide range of input scans, so I'm going to do an additional step of generating landmarks on each scan before loading it into my system. This landmark generation step will analyze each scan and create a series of points in 3D space. Then I can use these 3D points to more accurately and reliably build my mask creation system in the next step. There are a few open source landmark generators out there, but I ended up getting the best results with a Python-based solution in DeepMVLM. With that, I have all the 3D assets and processing workflow I need to get into my custom VR mask generation build. For the rest of the process, I'm going to be using Rhino 3D and its built-in node-based programming system, Grasshopper. Node-based programming is incredibly powerful for creating complex geometry. If you've ever used Unreal Blueprints, Cinema 4D, or Blender geometry nodes, then Rhino's Grasshopper will instantly look familiar. Likewise, if you have experience with parametric CAD software like Fusion 360, Onshape, or SolidWorks, then node-based programming is very accessible. Both parametric CAD and node-based programming can be thought of as a series of connected linear instructions that define and create 3D objects. Node-based solutions just expand on this concept and offer the ability to create more complex systems. From here I wanted to go through the mask generation in Grasshopper a little. I'm not going to cover every step in the process because that would take way too long, but I am going to go over the general high points of how this all works. You can see I have Rhino up here and Grasshopper open in the lower half of the screen with my definition all loaded up. The Grasshopper definition holds the complete instructions for creating a mask from any input face scan. All these nodes flow left to right. So I load in my scan on the left and have my finished ready to print mask geometry completed and output on the far right. This definition outputs a completed ready to print custom mask from the input scan into the same directory. This all works by loading in my face scan in this node over here. This will bring the 3D STL scan file into Grasshopper and start my generation process. This whole group of instructions is automatically bringing in the landmark points from the text file that I created in that last step I did. I have some basic logic built in here where if there isn't a matching landmark text file in that same directory as the face scan, the whole definition stops. I have safety checks like this built in throughout the definition, so if something goes wrong, the whole process doesn't keep going. In any case, you can see I have my face scan imported and my landmarks have been converted from text coordinates to points in 3D space. The key thing to understand about landmarks is that they'll always come into Grasshopper in the same order on any face scan. So anytime I select point number 45, that will always be the tip of the nose on a scan. Landmark 32 will be the center of the right eye, and 24 will be the center of the left eye, and so on. This is super important because it lets me position and build geometry off the scan in a reliable and predictable way. Now that my scan and landmarks have been loaded in, the next step is to do a basic orientation of the scan in 3D space. The overall size of the scan will always be spot on, but I don't have any great way of knowing the position of the scan when I load it into my 3D model space. This step will make sure that the scan is upright in my model space and on the correct side of the origin. I'm also rotating the scan data so it's at a comfortable level position without being tilted awkwardly up or down. This is actually one of those weirdly difficult things to get right. Some people have their head tilted a little back or forward when they're in their natural level eyeline resting position. I found a good trick is to generate a series of points from the chin to the forehead along the scan and then average a line through those points. Once I rotate this new line so it's vertical, that tends to be pretty close to a person's natural level gaze head position. It's not always perfect, but it seems to work pretty reliably and gives the quest a good natural resting position on a wearer's face. From here I want to move the scan data into the correct position relative to the frame hardpoint I designed in Fusion 360. That geometry is permanently stored in my Grasshopper definition at a fixed position in space. I'll just be aligning my scan data so it's a minimal distance from the frame for the build. So now I have the pitch of my scan correct and I have it placed at the same height as the center of my reference lenses. I have my eye distance from the lenses set at 19 millimeters in this version, and I can step the scan back if it's intersecting the frame from there. In any case, with that, my scan is oriented in space correctly relative to my Quest 3 frame. So now I want to clean up the scan a little before moving on to the actual mask construction. For most of the next steps, I'm going to be using a voxel plugin for Grasshopper called Dendro. Voxel-based geometry is a little different than traditional surface or mesh geometry and can be thought of as a three-dimensional pixel field defining an object. Voxels are great for smoothing and Boolean operations like combining two objects or subtracting one from another. Most importantly, voxel operations are very reliable, which makes them great for automated systems like this. So at this point I'm using Dendro to clean up my scan mesh. You can see in the before and after how effective the voxel pass was at cleaning up some of the chunky 3D scanning artifacts. I have to be a little careful here not to go too crazy with the smoothing process and lose face detail, but generally this is looking really good to continue on. Now I can draw in the actual mask surfaces that will make up the body of the mask itself. This allows the mask to adapt to each input scan correctly and build out a mask between the user's face and that frame. For the actual main body of the mask, I want to stick with a lattice structure for the build. The lattice structure will help reduce the overall weight, add breathability to the mask, and reduce the amount of resin I'm using on each print. The lattice framework's a little overwhelming in its final form like this, but I can break it down into a much more simple example to show what's going on. You can see here I have a simple quad mesh where each face has 4 sides. To get my lattice network, I'm taking all those edges and drawing in a bunch of points along each curve. From there, I'm using Dendro again to draw in little spheres at a specific radius. You can see if I lower my point density enough, you can see the individual little balls making up each strut. As long as I keep the density high enough, it'll come out as a solid tubular strut member. Problem is, when my lattice is in a basic grid like this, it looks pretty stagnant. Shape doesn't have any real direction or lead your eye anywhere, so it just looks kind of boring. If I change the quad squares to a diamond pattern, you can see the lattice network already starts looking more interesting. Right now all my struts are the same diameter though, but where this starts getting really fun is I can go in and change that so the diameter of the strut changes across each span. I'm setting a minimum and maximum strut diameter, then using a graph to interpolate that data. If I change the graph type, then each of my struts will change. This is really powerful stuff for changing the mechanical properties of a 3D printed material. If this part was going to be printed in a flexible material, I could change the springiness or dampen the impact of this part using this technique. I can keep progressing this as far as I want using these basic concepts. Here I've added a multiplier that changes those diameters based off the position of another reference point. All these logic steps are just building off each other to get a new, unique result. This process is the exact same thing that's happening back in the main mask lattice system. I'm just using an interpolation graph and defining my minimum and maximum strut radii. Each time a new scan is loaded in, the network will regenerate to fit that new face. Final step is the gasket lip. This is where the actual part comes into contact with the wearer's face and spreads the load of the mask out when the VR headset is worn. I added a larger surface area around the cheekbones in this case. The bulk of the weight of the headset ends up resting on the cheekbones, so a little bit of added surface area helps with comfort and stability. I've also added some texture to the gasket. The previous design used a stipple pattern here, but I decided to go in and make the texture out of a pattern of my logo to give the design a little subtle personality in the design detail. This texturing is really functional and important though. If this contact area was smooth, it would trap skin oil and sweat under the mask. So this texturing helps with breathability, prevents skin irritation, and helps a lot with long-term comfort. With all that done, I combine the voxel geometry and run a final smoothing operation. This cuts down any sharp edges and unifies all the geometry elements. And from there, the generation process is complete. There's one other feature I skipped over, and that's the glasses version of the design. Built into this whole Grasshopper definition is an alternate design that's made for people that wear glasses. This whole alternate build is triggered by the file name of the source scan. So this source scan is named cpiot for me. If that file name were cpiot-g, then the system would recognize that the glasses flag is on and do this alternate build. That design variation moves the wearer's eyes back for clearance between the Quest 3 lenses and the user's eyewear frames. It also adds 2 little notch cutouts for the arms of the glasses. As a final exercise, I added in a UI for batch processing scans. There's another plugin for Grasshopper that lets you make Windows GUI interfaces called HumanUI. This UI lets me point to a directory, then generate a custom mask for every scan located in that directory. I can also use it to tell me at a glance which scans have the glasses flag on and verify that all the landmark files are present. This all just shows how powerful this whole workflow is for creating on-demand consumer products. If I was doing this as a code-based solution, it would have taken me many hundreds of hours and be difficult to update and modify. By building this all in Rhino Grasshopper, it just makes it so much more easy to develop out, test, and run. This all seems like a bunch of steps to get a custom mask created, and on the back end at least, there's a lot going on. But now that the system is all set up, generating a new mask is a really quick process. I just use the iPhone's Face ID to get a 3D scan that is saved out as a mesh file. Then I create my landmarks so that I have both my 3D face scan and a list of landmark coordinates in a matching text file. From there I can just load my UI, point it at a directory, and generate my custom masks. The actual generation process is really quick with very little human interaction to create each custom product, which is pretty incredible. Now that I have a 3D file generated for my custom mask, I need to actually print it out for testing. I'm going to bring my mask over into Preform to do my slicing and prepare the custom masks for printing. I have a Formlabs Form 3 that I've been using on all my projects so far, but amazingly, Formlabs sent me a new Form 4, which I'm super excited to use. The Form 4 will let me print larger parts like this in a fraction of the time, which will really help with quicker prototype development. I'm going to keep the lip that interfaces with the Quest 3 facing down. This edge will be hidden by the headset itself, so I won't have to worry as much about support cleanup or anything like that. Looks like I have some minor cupping on the part. That's where there's an air pocket that will create a suction cup between the bottom of the resin tank, which can cause a print failure. These are looking pretty minimal though, so I'm going to go forward with the print for now. I may have to update the mask generator with some venting holes to fix this if it's happening consistently, but that's a future me problem. Besides that, everything's looking really good, so I'll upload this and send it off for my first print. The old mask I did for my custom VR headset a few episodes ago was taking over 12 hours per print. Here I'm looking at less than 3 hours for a single mask, so that's obviously a really great improvement. I'm also liking the integrated camera that's synced with the print process on the Form 4. I used to rig up an external camera to capture time-lapse videos of the prints, but this is much cleaner and doesn't require a bunch of setup time. The print came out great, so I'm going to do my usual IPA wash and post-cure in the heated UV light box. This is always my favorite part of a project. It's just so cool seeing something that was just a 3D model on the computer a few hours ago turned into a real-world object sitting here in my hands. I don't think I'll ever get tired of that. Alright, so I've got the existing MetaQuest here with the stock gasket on, and I'm just going to pop that off and then put on the new custom 3D printed version. Nice. Pops on just like a factory part, which is always super satisfying, but yeah, it's looking good. Super stable and locked in on there. Give it a roll. Yeah, it feels absolutely great. Yeah, I'm really liking the larger area over my cheekbones. It feels like it's really distributing the load of the mask and headset on my face evenly. And yeah, with the sort of normal stock foam gasket, you really have to sort of crank the headset down to compress that foam and make it fit evenly across your face, and that's what kind of causes those pressure points. This one, you really don't have to do that, which is amazing. I can actually loosen it up pretty significantly, so it's just barely feels like it's hovering on my face. And yeah, that's just because it's custom made for my face from that 3D scan. It's really just kind of a surreal feeling. It's like a perfect glove on my face, just sort of wrapping around me without even feeling like it's really there sometimes. It's really neat. And yeah, I really feel like I can sort of whip my head around really aggressively and not have it shift anywhere. Part of that comes down to the Quest 3 being lighter weight and a smaller form factor, but still, it's really nice, and I think the solid mask really helps stabilize everything on my face. Yeah, I was a little worried earlier on about making this out of a hard material, but it seems to be working out really well so far. The elastomeric one I made on the last VR headset was good and it's super comfortable, but it did feel like it would shift around if you really moved your head aggressively, just because it would flex. But this one, obviously because it's a hard material, just really feels locked in place, like it's not going to go anywhere. But yeah, I just couldn't be happier with the way this went for early stage prototype. It's really cool. Yeah, I can feel the ventilation coming through the sides. I don't have that sort of foggy feeling like there's air trapped in between my face and the VR headset, which is really nice, refreshing feeling for sure. Yeah, this is great. I'm going to go on and do some longer play sessions and other testing to see what it's like if I wear this for a couple hours or more, but early stages, this feels amazing, so I just couldn't be happier with the way it's going so far. I did some longer play sessions with the custom mask over several hours, and everything works surprisingly well. The breathability is fantastic because of the lattice construction allowing so much air to pass through. I also don't get any ski goggle-like pressure lines on my face like I would with a stock face gasket. This just turned into a really functional solution to the problem common with most one-size-fits-all masks. I think my takeaway with this project is that sometimes limitations make for better solutions. Because I didn't have many great options for 3D printing the custom VR mask in a soft, flexible material, I went the route of designing and making it in a solid one. This turned out to make for a way easier build and offer better performance in the end. Custom-generated consumer product systems like these really make it so you have to question all those basic assumptions about the features found in one-size-fits-all designs. All that said, there's more tweaks and improvements that can be made to this mask concept and more exploration to be done. Definitely going to be revisiting this one in the future and seeing what kind of new solutions are out there. This project was a fun glimpse into the future of industrial design, and it's going to be exciting to see how these concepts make their way into the consumer product industry in the coming years. Thanks for watching, and see you next time.